The night is the 13th of November, 1942, and somewhere in the grey, heaving waters of the North Atlantic, a German supply convoy is making its way through the darkness at 12 knots. The vessels are spread across roughly 2 miles of ocean. 7 merchant ships carrying fuel, ammunition, and machine components, escorted by 2 Kriegsmarine destroyers. Their commanders are confident. The weather is foul, visibility is near zero, and they are running without lights. On the bridge of the lead escort, a signals officer monitors the Funkmessungsgerät, the FUMO radar set, watching the sweeping green line for any hint of approaching aircraft or surface vessels. Nothing. The sea is empty. The convoy is alone. 4 miles to the northeast, at an altitude of just 300 feet above the wave tops, a pair of Bristol Beaufighter strike aircraft from 235 Squadron, Royal Air Force Coastal Command, are bearing down on the convoy at 300 miles per hour. Their pilots are wearing goggles against the spray and cold, their navigators crouched over instruments in the cramped rear cockpits. The aircraft carry 4 20mm Hispano cannons and 6 rocket projectiles each. They are also carrying something else, something the Germans do not yet fully understand, something that will cause the FUMO operator to glance at his screen one final time and see, to his complete bewilderment, nothing at all. The Beaufighters are coated, every inch of their upper surfaces and fuselage sides, in a substance the Royal Aircraft Establishment at Farnborough had spent the better part of 2 years perfecting. A substance deceptively simple in concept and profoundly clever in execution. A substance that would, in the months and years that followed this night attack, quietly revolutionize the tactical calculus of maritime warfare and render hundreds of Allied strike aircraft effectively invisible to German radar at the altitudes and ranges that mattered most. The Germans would come to call its effects radar absorption. The British, with characteristic understatement, called it simply anti-radar paint. The world would eventually come to know the concept as radar-absorbent material, or RAM. But the story of how the British arrived at this technology, the science behind it, the extraordinary men who developed it, and the convoys that vanished because of it, is among the most fascinating and least celebrated engineering stories of the Second World War. To understand why this technology mattered so profoundly, one must first appreciate the strategic nightmare that faced Allied maritime strike operations by the middle years of the war. German coastal convoys, supplying the Wehrmacht's Atlantic Wall fortifications and shuttling critical materials between occupied ports, had by 1941 developed a remarkably effective defensive architecture. The convoy routes hugging the Norwegian coast, the Dutch shoreline, and the Bay of Biscay were protected not merely by escort vessels and flak batteries, but by an increasingly sophisticated network of shore-based radar stations that could detect approaching aircraft at ranges exceeding 30 miles. Coupled with shipboard radar sets like the FUMO 21, which operated in the metric wave band and could detect low-flying aircraft at ranges between 8 and 15 miles, this system gave convoy commanders precious minutes of warning, enough time to bring anti-aircraft guns to readiness, to alert escorting fighters, to begin evasive maneuvers. The mathematics were brutal. An attacking Beaufighter or Beaufort torpedo bomber needed to approach at low level to avoid detection by high-altitude radar. But at low level, the shipboard radar sets were particularly effective because the radar energy reflected from a large metal aircraft at close range was enormous. Analysis of failed strike operations between 1941 and early 1942 showed that in roughly 67% of cases where convoys had been alerted before an attack, the element of surprise, so essential to the success of low-level strikes, had been entirely lost. Aircraft were being met by concentrated and accurate anti-aircraft fire. Loss rates climbed to levels that could charitably be described as unsustainable. During the spring of 1942 alone, Coastal Command lost 43 aircraft to anti-aircraft fire in convoy strike operations, a rate that threatened to extinguish entire squadrons faster than operational training units could replace them. The challenge seemed insurmountable. Simply flying higher defeated the purpose of low-level attack. Flying faster was constrained by the capabilities of existing aircraft. Attacking at night introduced its own navigational and targeting complications. What was needed was a way to make the aircraft itself less visible to the radar that was getting them killed, not invisible precisely, for that was the stuff of fantasy, but sufficiently reduced in radar signature to deny the enemy those critical extra minutes of warning. The solution emerged, as so many wartime solutions did, from an unlikely intersection of academic science and urgent operational necessity. The theoretical groundwork had actually been laid in the 1930s, when Dutch physicist Hendrik Casimir, working at the Philips Research Laboratories in Eindhoven, had explored the electromagnetic properties of certain carbonyl ion compounds. Casimir's work was essentially pure physics. He was interested in the behavior of ion particles at the molecular scale when exposed to radio frequency radiation. He was emphatically not thinking about aircraft, but the underlying principle he had identified, that certain materials with specific magnetic and dielectric properties could absorb, rather than reflect, incident electromagnetic radiation, would prove to be exactly what the engineers at Farnborough needed. The Royal Aircraft Establishment at Farnborough had been aware of German radar capabilities from at least 1940, when intelligence assessments first confirmed that the Kriegsmarine was deploying shipboard radar sets operationally. Dr. Frederick Brundret, a physicist who had moved from the Admiralty Research Laboratory to a senior advisory role with the Ministry of Aircraft Production, was among the first to formally articulate the possibility of radar-absorbent coatings for aircraft. Brundret's background was in electromagnetic theory, and he had followed the pre-war European literature closely enough to be aware of the Casimir work, even if imperfectly. In the summer of 1941, he wrote a memorandum, now held in the Public Record Office at Kew, that outlined in general terms the possibility of treating aircraft surfaces with materials capable of converting radar energy into heat through molecular friction. The memorandum was remarkably prescient. It was also, at the time, treated with a degree of skepticism by colleagues who considered the practical engineering challenges prohibitive. What changed the institutional attitude at Farnborough was a combination of worsening operational losses and a specific piece of captured German intelligence. In the autumn of 1941, fragments of a German Schnorkel-equipped U-boat that had been depth-charged in the North Atlantic were recovered and analyzed. Among the more curious findings was evidence that sections of the U-boat's conning tower had been coated with a rubberized material embedded with iron oxide granules. The British initially assumed this was some form of anti-corrosion treatment. Closer electromagnetic analysis suggested otherwise. The material appeared to have been specifically engineered to absorb centimetric radar radiation, a startling discovery, as it suggested the Germans had already made significant progress in radar-absorbent material research, most likely to reduce the radar cross-section of U-boat conning towers against Allied ASV, to surface vessel, radar sets. This galvanized Farnborough. The Germans, it appeared, had arrived at a similar theoretical conclusion from a different direction. If the enemy was already applying radar-absorbent technology to their submarines, the technology was clearly practical. The question was whether it could be adapted and applied to aircraft, a considerably more demanding engineering challenge, given the constraints of weight, aerodynamic smoothness, adhesion at altitude, and the vastly greater surface areas involved. The man tasked with solving this problem was Dr. Eric Eastwood, a physicist who had joined the RAE in 1938, after completing postgraduate research at Cambridge under the supervision of J.A. Ratcliffe, one of Britain's foremost authorities on radio wave propagation. Eastwood was 31 years old, quietly methodical, and possessed of the particular intellectual quality most valuable in wartime research, the ability to translate theoretical possibility into practical engineering specification. He understood both the physics of electromagnetic absorption and the operational requirements of the aircraft that would need to carry whatever he developed. He also had access, through the RAE's network of industrial contacts, to a range of materials suppliers and coating manufacturers who could assist with experimental formulations. The physics that Eastwood was working with were, at their core, an application of what engineers now call the Salisbury screen principle, though Eastwood was developing his approach independently and in parallel with similar work being conducted in the United States by Winfield Salisbury himself. The fundamental concept is deceptively simple. When electromagnetic radiation, radar energy, strikes a metallic surface, it is reflected back in the direction of the transmitter. This reflected energy is what the radar receiver detects. To reduce that reflection, one must either scatter the energy in non-useful directions, shaping, which is the basis of modern stealth design, or absorb it, converting it into heat. Absorption requires a material with specific electrical and magnetic properties, a material with both resistive loss, which dissipates energy through induced electrical currents, and magnetic loss, which dissipates energy through the oscillation of magnetic dipoles within the material's molecular structure. Eastwood's experimental program, which ran from late 1941 through most of 1942, explored a range of candidate materials. The most promising were compounds combining carbonyl iron produced by the thermal decomposition of iron pentacarbonyl, yielding particles of extraordinarily uniform size and shape, with various organic binders. Carbonyl iron had the desirable property of extremely high magnetic permeability at radio frequencies, combined with manageable electrical conductivity. The trick was formulating a compound that could be suspended in a paintable medium, applied to aircraft surfaces, and would adhere reliably through the thermal cycling, vibration, and moisture exposure of operational flight. The early results were encouraging, but imperfect. The first test formulations applied to scaled aircraft models in Farnborough's electromagnetic test range, a facility that would today be recognizable as a primitive anechoic chamber, showed reductions in radar cross-section of between 15 and 30%, depending on the radar frequency band and the angle of incidence. This was promising in absolute terms, but operationally it was insufficient. A 30% reduction in reflected power corresponded to only a modest reduction in radar detection range. The relationship is logarithmic, and in practice, a 30% reduction in reflected energy might reduce detection range by perhaps 15%. Useful, but not transformative. What changed the picture was a refinement in understanding of the specific radar frequencies the Germans were using. British signals intelligence, drawing on intercepts of Kriegsmarine communications and analysis of captured radar equipment, had by mid-1942 established that shipboard German radar sets, including the Fumo 21 and its successors, operated predominantly in the metric wave band, specifically in the frequency range of approximately 125 to 180 MHz. This was crucially different from the centimetric wavelengths used by British ASV radar. The distinction mattered enormously because the optimal absorber material composition depends heavily on the target frequency. Specifically, the particle size of the iron compound must be scaled to produce resonant magnetic loss at the frequencies one wishes to absorb. With the target frequency clearly defined, Eastwood's team was able to optimize their formulation specifically for the 150 MHz range. The result was a paint comprising carbonyl iron particles of carefully controlled mean diameter, approximately 1.5 micrometers, suspended in a chlorinated rubber binder with a total dry film thickness of approximately 1.2 millimeters. This formula, which the RAE designated internally as Material Type R, achieved radar cross-section reductions of between 60 and 80% in bench testing at the target frequencies. In operational terms, this translated to a reduction in detection range by the Fumo 21 of roughly 50 to 60%, from a nominal detection range against a Beaufighter of approximately 12 miles down to 5 or 6 miles. At an approach speed of 300 miles per hour, this represented a warning time reduction from roughly 2.5 minutes to barely 1 minute. It was, for the radar operators of the Kriegsmarine, the difference between a carefully prepared reception and complete, catastrophic surprise. The manufacturing challenge was substantial, but not insuperable. Carbonyl iron in the required particle size and purity specification was not a standard commercial product, but it could be produced in sufficient quantities by British Metal Carbonyls Limited, a subsidiary of the Imperial Chemical Industries Complex, which had pre-war experience in fine iron powder production for other industrial applications. The chlorinated rubber binder was a standard product of the British rubber industry. The formulation was compounded at a pilot facility in the Midlands, and the resulting material, which had the appearance and handling characteristics of a conventional grey paint, could be applied by standard spray equipment operated by ground crew with no specialist training. The weight penalty was a legitimate concern. A full application of material type R to a bow fighter, covering the fuselage sides, upper wing surfaces, and tail assembly, the surfaces most likely to present a significant radar cross-section when approaching at low level, added approximately 40 to 55 pounds to the aircraft's operating weight. For an aircraft with a maximum takeoff weight of 25,200 pounds, this was a penalty of roughly 0.2%. Insignificant in aerodynamic terms, completely acceptable from a structural standpoint, and entirely worth the operational benefit. Squadron commanders, initially skeptical of any modification that might compromise performance, were generally persuaded once the weight calculations were presented. The operational introduction was gradual and deliberately understated, which was, of course, exactly the right approach. There was no point in drawing German attention to the modification by any public acknowledgement or dramatic announcement. The coatings were applied to aircraft at squadron maintenance level, incorporated into the routine repainting schedule that kept Coastal Command aircraft in their maritime camouflage schemes of dark slate grey and dark sea grey. To a German intelligence analyst examining photographs of British aircraft, or even to an Allied pilot unfamiliar with the program, a bow fighter treated with material type R was visually indistinguishable from any other bow fighter. The additional 1.2 mm coating was invisible. 235 Squadron, operating from Chivenor in North Devon, was among the first units to receive the modified aircraft in the late summer of 1942. Their primary operational area was the Bay of Biscay and the approaches to the French Atlantic coast, where German supply convoys and blockade runners represented priority targets. Strike operations in this area had been particularly costly, with German radar coverage both from shore stations and escort vessels providing reliable early warning. The squadron's operations record books, now held at the National Archives, chronicle the transition with the measured factual tone characteristic of RAF documentation. What they record, in the aggregate, is a striking improvement in strike success rates. Between August and November of 1942, the period during which material Type R-equipped bow fighters of 235 Squadron conducted the majority of their strike sorties, the proportion of attacks achieving complete surprise, defined as reaching the target convoy without triggering defensive fire before the attack run, rose from approximately 35% to over 70%. Loss rates to anti-aircraft fire fell correspondingly. No single sortie could be attributed definitively to the coating's effect, of course. Weather, crew skill, route planning, and sheer fortune all played their roles. But the statistical pattern was clear, and it was consistent across multiple crews and multiple operations. The German response, when it came, was characteristically thorough and ultimately only partially successful. Kriegsmarine signals intelligence began noting, from the late autumn of 1942 onwards, a pattern of radar contacts that appeared and disappeared in anomalous ways. Contacts that should have been detectable at 15 miles appearing instead at 6 or 7 miles, or contacts that were apparently lost and then reacquired at unexpected bearings. The operational interpretation was initially that the British were employing some form of jamming or electronic deception. Interrogation of captured Allied aircrew, who in most cases genuinely did not know the full details of the modification to their aircraft, produced inconclusive results. It was not until a bow fighter from 235 Squadron was forced down relatively intact near the Brittany coast in early 1943 that German technical analysts were able to conduct a thorough examination. What they found perplexed them initially. The unusual grey coating was scraped and analyzed by scientists at the Forschungsanstalt der Deutschen Reichspost, the German Postal Research Institute, which was heavily involved in radar and electronics research, and identified correctly as an iron-based radar-absorbent compound within a matter of weeks. The technical principle was not, after all, unknown to German science. The challenge the Germans faced was more practical than theoretical. Applying similar technology to their own aircraft would require a production infrastructure for the necessary fine iron powders that did not currently exist at the required scale, and would require development of operational procedures for routine application that would take time to implement across a dispersed Luftwaffe maintenance system. The Germans did eventually develop their own version, designated Schornsteinfeger, literally chimney sweep, a reference to the material's dark appearance and associated with the idea of sweeping away radar returns. But the timeline was long, the application was inconsistent, and the strategic moment, in some respects, had already passed. By the time Schornsteinfeger-treated aircraft were appearing in meaningful numbers, the broader balance of the air war had shifted in ways that made tactical radar evasion a less decisive advantage than it might have been in 1942 and 1943. The Americans, who were briefed on the British development through the Combined Intelligence Network in early 1943, developed parallel programs with characteristic energy and resource. The National Defense Research Committee's Division 15, responsible for radar countermeasures, had been pursuing radar-absorbent materials research since 1941, but had focused primarily on centimetric wavelengths appropriate to the American AN/APS-3 radar systems. The British sharing of material type R specifications enabled the Americans to adapt their research to metric band German radar frequencies considerably faster than they might otherwise have managed. The resulting American formulation, designated NC-503, was applied to elements of the anti-submarine aircraft force operating over the Atlantic and contributed to the reduction in U-boat warning times that complemented the broader Allied anti-submarine campaign. The strategic impact of British radar-absorbent technology, assessed with the benefit of hindsight, falls into the category of significant but not decisive, an important edge in a contest decided by many edges working in combination. Statistical reconstruction of Coastal Command convoy strike operations for the period 1942 through 1944, drawing on post-war German and British records, suggests that material type R-treated aircraft achieved surprise attack conditions roughly twice as often as untreated aircraft on comparable sorties. Given that surprise was broadly correlated with both strike effectiveness and crew survival, the compounded effect over hundreds of sorties was substantial. The number of Allied aircrew who survived operations they might not have survived without this technology cannot be calculated with precision, but the aggregate clearly runs into the hundreds. The technology's influence extended well beyond the war itself. The theoretical and practical foundations established by Eastwood and his colleagues at Farnborough formed a direct intellectual lineage to the post-war development of radar-absorbent materials that would ultimately culminate, decades later, in the stealth aircraft programs of the United States and other nations. The fundamental physics had not changed. The insight that electromagnetic absorption could be engineered into a material's molecular structure, applied as a coating, and exploited operationally remained as valid in the 1970s, when Lockheed's Skunk Works began serious stealth research, as it had been in 1942. The men who designed the F-117 Nighthawk's surface coatings were working with infinitely more sophisticated materials and computational tools than Eastwood had possessed, but they were exploring the same electromagnetic territory. What had changed was the context of application. In 1942, the requirement was to reduce radar detection range by a tactically useful margin at a specific frequency band, using materials that could be manufactured in wartime Britain and applied by squadron ground crew. In the 1970s and beyond, the requirement was for far greater reductions across much wider frequency bands, achieved through the integration of shaping, advanced composites, and highly sophisticated absorbent materials engineered at the molecular level. The Farnborough work was not a roadmap to stealth, but it was a proof of concept, a demonstration that the basic principle was operationally viable, that it could be engineered into a practical system, and that the benefits, though difficult to measure with precision, were real and significant. Several physical examples of material Type R and related wartime radar-absorbent coatings survive in museum collections, though they are not among the more celebrated exhibits of Second World War technology. The Science Museum in London holds samples of the original Farnborough test specimens, catalogued in a collection of electromagnetic materials research from the period 1940 to 1945. Farnborough itself, now the home of the Kinetic-U research establishment, preserves institutional archives that include portions of Eastwood's original research notebooks, documents of considerable historical and technical value, though accessible only to researchers with appropriate clearances for certain portions of the material. The aircraft of 235 Squadron are long gone, lost to the attrition of wartime operations and the scrapping that followed the armistice. No bow fighter treated with material Type R is known to survive in airworthy condition or in museum preservation, though the Bristol Aero collection at Kemble holds a Beaufighter Mark X in reasonably complete condition that has been the subject of ongoing historical research. Whether any traces of the coating chemistry survive on any known preserved aircraft is a question that has not yet been fully answered. The analytical techniques of modern conservation science, including X-ray fluorescence spectrometry and scanning electron microscopy, could theoretically identify the characteristic carbonyl iron particle signatures if they were present, but systematic examination has not been carried out. Dr. Eric Eastwood went on to a distinguished post-war career in electromagnetic research, eventually becoming chief scientist of the Marconi Research Center and making substantial contributions to the development of civilian radar meteorology. He was awarded the OBE in 1953 and the CBE in 1966, the citations making no specific mention of his wartime work, which remained classified for many years. He died in 1981, and the obituaries published in the scientific journals of the time alluded in general terms to important contributions to radar research, without specificity. It was the appropriate fate of a man whose most significant achievement had been, quite literally, to make things disappear. The story of wartime radar-absorbent materials is, at its deepest level, a story about the asymmetric power of information in technical competition. The Germans had the radar. The British could not destroy the radar, could not jam it reliably, and could not avoid it by flying differently. What they could do, with a few kilograms of carefully formulated iron powder and chlorinated rubber applied with a spray gun, was change the fundamental terms of the encounter. They could not make their aircraft invisible, but they could change the moment of revelation, push back the instant of discovery by seconds that translated into the difference between a disciplined anti-aircraft barrage and a scattered, desperate response. In the mathematics of combat aviation, those seconds were worth lives. That is perhaps the most enduring lesson of this technology and of the extraordinary men who developed it under extraordinary pressure. The most powerful military innovations are not always the most dramatic. They are sometimes a coat of paint, a carefully considered, precisely formulated coat of paint, applied in darkness on a rain-sodden airfield in Devon, by mechanics who may never have known quite what they were doing, preparing aircraft to fly into the night and vanish for one vital minute from the screens of men who had every reason to find them. The convoys, for a time, could not see them coming. That was enough.